if you want to give it. Let me actually, what I'd like to start with, actually, which maybe is actually kind of fun. Again, before I get into the real things that I want to talk about, actually, people are starting to collect. Okay. I wanted to talk about, last class I mentioned in a hurried way, this idea that, the importance of visualizing your data. We're dealing with time series data in here. I mentioned this guy named Edward Tufte and his books on visualizing information. And I showed you one example of that last class, of some data that how he took a typical data collection of PowerPoints produced by typical researchers and showed how you could make something what is, I think, infinitely clearer and more revealing than is sort of just the default thing that comes out of a PowerPoint presentation. And I strongly encourage people to look at and read his books. They're fun books. They have lots of pictures in them. Yeah.
I'm not aware it's supposed to go on. Not only does he have the fun books, but he also wrote a short pamphlet essentially about learning how to do.
Right. So he's written lots of interesting things. One is about why PowerPoint is evil. And one of the ways that he proves that PowerPoint is evil, okay, he has his pamphlet about it. But one thing that he does is, whenever there's a scientific event in the world that seemingly went wrong, okay, he will go back and take a look at the data that people presented and reanalyze it somehow to show that it's a better way of doing it. So one example was when the first space shuttle blew up, okay, that you had a world where there was a space shuttle, okay, that they had, some of you were probably not born then, I need to say, okay, but that they had a situation where they launched the space shuttle 50 times and it had gone off, and one day they decided to launch it at a much colder temperature than it had ever been launched in before. And the engineers desperately went to management and said, the space shuttle is going to blow up, the space shuttle is going to blow up. And he gave them data, and he showed them a PowerPoint presentation. And the management listened to the presentation and said the engineers are crazy. And then the shuttle blew up. And so one thing that Tufte did was then take a look at their data and regraphed it in such a way that it was obvious the space shuttle was going to blow up. And that sometimes the reason why the space shuttle blew up, if you interpret this, is that they did a lousy job of data preparation. Possibly you can blame it on PowerPoint, okay? But it was a question of not making a plot that showed what happened, the issue. Then 10 years later, another space shuttle blew up, okay? And what happened? Right before, during the course of the launch, something had happened to damage some of the tiles. Some foam had fallen off and hit some of the tiles, the heat shield tiles. And the engineers looked at this and said, this is going to cause terrible damage. The space shuttle is going to blow up. And they showed all kinds of data about the impact damage caused by the foam and stuff like this. And management looked at their data and listened to it and said, you guys are crazy. And they let the space shuttle come down and it blew up. I guess it melted down. It didn't blow up, I guess. Okay? And again, Tufte then took their data and regraphed it. And when you look at the graph that he draws, suddenly you can see, yes, it is a big risk to have foam this big fall down on it, okay, based on the data that you already had. So knowing how to visualize data so that it's clear and understandable and meaningful is an important thing. It may not seem like a hardcore thing, but it really is important. And just to give you a taste of what he does in his books, because I think it's actually really interesting, I took some figures from some of his books showing what he considers to be good and bad time series plots. Okay? This is an example of what he considered to be one of the worst time series plots that ever appeared in print. Okay? What is this, to be precise? Again, you can't really see so well because of the digitization issue. But this is, if you look at it, it's measuring something about, I think it is wealth or income as a function of people who are below 25 years old or over 25 years old. Okay? Or no, so the probability of having a certain thing happen, whether you are above a certain age or below a certain age. And there are my spot is really bad right now. It looks like there's 1, 2, 3, 4, 5 different data points plotted. Okay? And in this plot, what he did, the artist did, was first of all, he drew it with these curved figures interpolating through 5 points, where the curves mean nothing. He had these shadows here. These you've probably seen when you use PowerPoint. There are these special effects where you make your bars in 3 dimensions, right? You make them rectangles. That's really cool. But what does that actually add to the presentation of the data? In fact, these blue and red and green things are simply shadows cast by this object that he formed, okay, from these 5 data points. And what's further is because this is somehow corresponds to a case of, I don't even remember what the data is, but it turns out that these points are basically 1 minus these points. Okay? The data up here is completely revealed by the data up here. Okay? I think they're like mirrors. It looks like they're mirrors. That's basically what it is, if you look like it. Right? And if you believe that, then there's no reason to have this thing up here. The only data really visible here were 5 points. And everything else, sort of adding the color and adding the dimension and all this kind of stuff, basically obscures that. Any questions about that? Here was another plot that he had that came from a newspaper that he thought was terrible. This was mentioning news, giving you a plot of what were the laws of in the United States concerning fuel economy. How much miles per gallon did cars have to get as a function of time? Okay, and they very cleverly put it on a road. But what is the data here? Okay, can anybody see what the data of this graph really is? Okay, what they're trying to show you is that as time goes by, these are years, 1998, 99, 80, 81, 82, 83, 84, 85. This is what the fuel economy is. So they're showing that as time goes by, the standards are getting more demanding. Now, what is misleading about this graph? Okay? Or is there anything that's not misleading about this graph? Okay? People see what in principle is the data that's being presented. It's presenting fuel economy as a function of time. Okay? Now, what does this graphic do for you? Okay? It's misleading for several reasons. First of all, if you look at it here, this here was 18 miles per gallon that year. Here it was 27.5 miles per gallon, right? Because of this skew, it looks like this is a really big increase in size over that, right? Okay? But in fact, it's only like a 50% thing. But this line is really sort of, 300% times bigger, right? These lines, if you look at it, are not equally spaced. They correspond to years, okay? In principle, what would be a much better representation of this data, in a way to see how fuel standards are increasing or decreasing, would be an x-axis of equally spaced years, and a y-axis where the height of the bars correspond to the numbers that you're trying to show, right? And then what would you probably see here? You would probably see, is this growing linearly or is it not growing linearly? Okay? It looks like, is it slowing down? Is it increasing? Things like that. That would be what would be a much better visualization. Any questions? Again, I point this out because one of my pet peeves with my students is that when we often in the course of doing research, you generate experimental data. And how you plot it to see what's going on is an important issue, okay? And it's very easy to get dumb plots, okay? These maybe are dumb plots people had to work hard to get, but it's very easy to get misleading plots to show what's going on. Let me just show you one example of what he considers to be a good kind of presentation of data. And this is actually one that I think is very, very clever, okay? And it's one of the reasons why one should read his book, because it's not a clever idea. It sensitizes you to what makes data interesting. What is this plot? Okay? This plot actually is of a railroad schedule. Okay? This is showing you the time that trains are going between Paris and Lyon. It's an old map. This is, I guess, Paris. This is Lyon. And what is he actually doing? How come is a train schedule how could a train schedule be thought of as a time series? If the x-axis is time, the y-axis for a train would represent where is the train actually on this line. Does everybody get that idea? So you could think of a train schedule as a what do you call it? As a time series. If you figure that at a particular time the train is here, let's say it's going from Paris to Lyon, it's going to travel at a certain rate of speed. If, let's say, there's going to be a stop at a station for a lunch break, the train is not going to be moving over that time, right? And if the train keeps moving. So what's interesting about this is showing you all the trains from Paris to Lyon. And this axis is position. This axis is time. Okay? You've all seen, I think, train schedules, but you've probably never seen a train schedule like this. What makes a schedule like this interesting? You can see things in this kind of a representation of a train schedule that you can't see in a normal train schedule. What would be a way to figure out which is the fastest train? Can anyone show me which is the fastest train from Paris to Lyon? Okay, how would you tell from looking at this kind of a plot? Okay? What would be the phenomena that you would be looking at? Each one of these lines corresponds to a train that's doing its thing. Which train is fastest? Okay? What would be the property of the fastest train? Yes?
One shows the
Steepest slope, right? So now if I look at this, I want to get there as fast as possible. I hate being on trains, okay? The steepest slope one, which one is that? These look pretty steep to me for some reason, okay? These look steeper to me than this one. That tells me that that's probably a faster train, right? What other properties can you tell? Which trains stop moving? On Long Island, what I take, I have a couple people here from Long Island, okay? The Long Island Railroad occasionally stops because you have two trains using the same track. And it's really annoying to sit there on a train that stopped because they're not using, you know, it'd be more annoying if the two trains used the track at the same time, because then they would crash. But how can you figure out which train is stopped? Okay, which trains have stops on where they sit and idle for a while? What is an idling shown by? Okay, it's shown by flat regions. This one here clearly idles for some reason. Okay, perhaps it looks like it waits at in fact, since these are stations, unlike the Long Island Railroad, it idles at a station as opposed to a sort of a siding off the track. Okay? When will you be able to reach your hand out and get it cut off by a passing train? Okay, or wave to the train as it goes by? How can you figure that out? What? When they cross, right, okay. Any point of intersection. Any point of intersection here means that you're going to see a train out the window on the other track, right? And how do you tell which trains go in one direction versus the other? It's whether they have a positive slope or a negative slope, right? So this, to me, you should agree, I think, is a clever visualization of a set of data that lets you see things you wouldn't otherwise see, okay? Now, obviously, it hasn't caught on the railroad schedules of the world. But it's sort of a good model of, again, what you might be able to do with a good visualization to see things you wouldn't otherwise see. And if you find these interesting, again, I strongly recommend you look up Tufte's books, okay? Because they're a lot of fun to read. Any question? Well, this particular graphic is 100 years old. So the answer is quite possibly it's not used on contemporary trains, okay? But it is, again, it should be clear that if you want to study certain properties of a train schedule, okay, it has interesting properties. Why would this not be a good train schedule? What would be a bad thing about, if let's say they printed this in the train schedule, why do people like other train schedules better?
For one thing, trains are locals and expresses, and it's very difficult to tell what's local and what's express.
So one problem here might be you're saying that in this model you couldn't tell a local from an express. Is it going to stop someplace? That's probably not a flaw of the design, actually, because first of all, if it stops, that might show up as a delay here, okay? Or you could conceivably put points on the, on the lines where you stop, okay? I would say a bigger probably problem with this is that it doesn't tell you exactly what moment you have to be at the station, right? When you look at a train schedule, it says you have to be there at 8:53. You're reassured. This says that it's going to be, you have to look it up and interpolate a little bit, okay? So if you want the illusion of precision, you may have problems with that. Any questions? But the important point here is not why aren't train schedules like this. The important point here is that there are interesting ways to visualize and represent data, and you should sensitize yourself to this. Any questions? Okay. What I'd like to do before I go any further, is, in the material for today, is ask if there are any questions about homework 1. Several people emailed me questions, and I deliberately did not answer them so that they could be discussed in here. How many people have started work on homework 1? Okay, a couple of them. Okay, good. Okay. Any questions or issues about homework 1 that you sent by email? Okay. Yes.
So in the second question, the fraction formula, I found that you didn't give us about the year. It's the y in the
Okay.
formula.
Right. So one question here is, again, what is the homework 1? The homework 1 is that I give you a bunch of data on stock and stock prices and options, and I tell you, come up with, compute an estimate of what the value of a given set of options are, and then compare them to the price they were actually trading at that instant, and see if you learn something from it. That's basically the assignment. Now, the one parameter I did not give you was the yield, which is the dividend value. Okay, I would say there's two ways you could handle it. One way is to assume that the dividend yield is 0. Okay, that none of these stocks may be offering dividends. The other possibility, if you want to be extra precise, would be to go back and take a look at, there's only like 5 or 7 stocks that all the options are drawn from. You could conceivably go and do some research on your own and figure out whether or not any of them are actually offering dividends. Okay? But my simplifying assumption would probably be to say that the dividend yield should be set to 0. Okay? Yes?
For the EWMA model, you could also use that for estimate the volatility in both pricing models. But what is the requirement of the days in expanding that series?
Okay, so what I want you to do, again, the purpose of the assignment is I want you to sort of, again, try to build as good a model as you can for pricing options. You may want to play with a couple of different ways of thinking about it to see how well they fit the observed data. You do have options prices, the actual real options prices, right? So one way to assess whether or not a model is good or bad is going to be to see is the error, the difference between your predictions and what the actual model, is it get better or worse as you tweak something? That's one way to experiment with it. But now your specific question has to do with how we calculate volatility, okay? And I guess I suggest that you try 2 different methods for calculating volatility. One of them was the exponentially weighted moving average, and the other was just a standard deviation of some history of returns in the back. Is that correct? Okay. What was your question now?
Because there is a factor called N in using EWMA, right?
There is by a factor, what is the decay factor? Okay, say that again.
Not the alpha factor. I'm just talking about how many days do we need to consider in using EWMA.
Okay, we'll talk about the EWMA algorithm. We'll talk about volatility modeling today, hopefully. So if in fact, with 20 minutes to go in class today, I haven't started talking about volatility modeling, you should yell, okay? Yes.
Another question is that you can see that all the options provided by you are American options. Why do you still require to estimate it in Black-Scholes model?
So basically what I want you to do is to experiment with it, okay? That's basically, I guess, the interesting thing. And those are the 2 models that we have, simplest models that we have talked about in here. So what you're saying is actually that the Black-Scholes may not be right for pricing American options. Okay? Put in the numbers, see what happens, and see how accurate it is or is not. That's kind of the interesting thing that I want you to try to do. In principle, we've talked about a couple of ways of pricing options. The purpose of the assignment is for you to decide, do they do a good job or a bad job? Okay? And how well do they do? Okay? Any other questions about the assignments? Okay, yes?
I just want to know the stock price. What period is that stock price for? Is it from when to when? So you just give us some stock price day to day, but not another period.
Okay, you mean that I didn't tell you what day?
Yes.
Okay, I believe that the date it is supposed to be is from the date that it's supposed to be from is the day of the basically the option. So all that data was collected on the same day. Okay, meaning that that it was collected so that that stock data would be relevant for pricing those options. There was a current date given for those options. Is that correct? Okay. So my belief is that my recollection is that the prices should be from basically that day or the day before going backwards. And the easiest way to check is just to align it. If you're a little bit concerned with that, go ahead and check with one of the financial databases to see if that's actually right. But it's intended to be the past from the relevant past from the time that you're pricing the options. Any other questions about that? Yeah.
So you give us many interest rate of many days, but you didn't give us the exact day of the option price.
So what we did was give a couple of different interest rates, again quoted at the time of somehow there's a moment right now when you're trying to price the options. Those interest rates should correspond to what are the available interest rates in that class on the current date when I'm asking you to price the options, which may be like September 19th or something like that, right? So you should interpret that as being the interest rates that are available today, where today is the day that you're pricing the options. Does that answer your question? Okay. Any questions? Now there's some question of which rates are relevant. Okay. And that's something for you to think about and figure out and play around with. Okay, that's part of the modeling effort here. Okay? So one simple question would be to try each one and see which does best. Okay? But perhaps, another question might be to look at them and think which of them makes sense, as the most sense, as the interest rates that should be used in that time. Okay? Any questions? So the goal is hopefully you'll be able to see that yes, you can grossly price these options. That's the intention. Okay? And to see how accurate or not, developing a feel for that is what the whole purpose of the assignment is. Any other questions about homework 1? Okay? And has anybody implemented the programs? Both of the programs yet? How many lines of code did it take to do it?
Just 200.
Okay? Just 200, you said. Anybody else? Somebody else has implemented it. How many lines did it take them? Anybody else implemented yet? The 2 programs? Okay? It says 200 there. So that's a sign that gives you some scale as to what the level of effort is. Any questions? Okay. Let's then move on at this point. Okay, so what I'd like to talk about now, we've been talking here about time series analysis. And what I would like to talk about now is get into the question of correlation. So my goal for today is to start talking about correlation and to start talking about, let's say, modeling techniques for time series. Okay, but correlation is one of the, let's say, very important tools for understanding what a time series is actually doing. Okay? So we've talked several times in here about variance. The variance of a random variable, okay, which is the square of the standard deviation, is defined as the difference, the square of the difference of the random variable minus its mean, okay, divided by the number of samples, okay? And when you compute variances, okay, one thing that you find when you statistically compute variances, sometimes there's a question of whether or not you're dividing by n or dividing by n minus 1, n being the number of terms in your time series. Okay? There's let's say, a reason why there is some debate or an issue about whether you divide by n or n minus 1. N seems like the logical thing to be doing because you're taking the average of n terms. Okay? And so dividing it by n seems to make sense. When you look at a statistics book and they say, what is the sample variance? The variance of a sample if you have observed data. They will often suggest dividing it by n minus 1 instead of n. Okay, and that always looks weird. The reason for that turns out that if you if you're taking sample data, okay, you're computing your variance based on a sampled mean. Okay, if you look at the mean, the question of the difference in the values minus the mean. If you're dealing with sampled data, okay, you're getting an estimate for the mean as opposed to the absolute outlying mean. Okay? So there is in some sense potentially some error in your mean estimate. And since you're somehow measuring your error distance from this sampled mean, okay, if you want to produce an unbiased estimate as what the variance is, it turns out you can prove that dividing by n minus 1 turns out to be the right thing. Okay? So if you've ever seen variance formulas, that's sort of the argument as to why you sometimes see it with n and why you see it with n minus 1. My recommendation is you work with time series that are large enough that n minus 1 and n are about the same thing. And then the point doesn't really matter very much. Any questions? Okay, so that's our notion of variance. More interesting when we talk about, let's say, in correlation analysis, is something that we talk about called the covariance of two random variables. Suppose I have two, let's think of them as time series. Okay, two time series sampled at over the same time interval. So you have n points each. Okay? The covariance of these two random variables is the an expected value of each sample minus the mean of the ith sample of the x of the first time series minus the mean for the x time series times the ith sample of the second random variable time series minus its mean. So what does the covariance ants measure? Okay? It measures, in some sense, a function of how in sync two random variables are. So what happens? If, let's say, we're interpreting it as, let's say that the ith value of both time series, okay, are above their mean. Okay? It's a good time at time I for both of them. Then x minus the mean for x, x sub I minus the mean for x sub I is going to be high. Y sub I minus the mean for I is going to be high. Y is going to be high. A big number times a big number is a big number. If x is low, is very negative, is below the mean, okay, it's small, x minus the mean is negative. If y is below the mean, y sub I is below the mean, y minus the mean is going to be negative. A negative number times a negative number is a positive number. So if both time series are down low, okay, they are going to have, again, a large positive contribution to the covariance. It's only when one of the signals is above the mean, their mean, and one of the signals is below the mean, that you get a negative contribution to this sum. Okay? And if the signs really didn't matter at all, the probability that if the two variables were independent, x sub I being above the mean wouldn't have any impact at all as to whether y sub I was above its mean. So you would sort of think, if you're summing up these terms over all the time series, if the two variables are in sync, this covariance is going to be very high. If the two variables are completely out of sync, okay, let's think about that. What if it's going to be if two variables are out of sync? That one of them is always high and the other one is, when one of them is high, the other one is always low. Then all the terms would be negative. Okay, you would have a negative. One would be below the mean, the other one would be above the mean. All the terms would be negative. The magnitude of it would still be very large. Okay? So what we end up getting here are, if the variables are in sync, either positively correlated or negatively correlated, the covariance is high. If they're independent, everything cancels out and the scores are around 0. Any questions? So the correlation coefficient, okay, is basically this covariance of two series divided by the square root of their respective variances. And that sort of normalizes the covariance, okay, in such a way that you get a quantity between -1 and 1. 1 means that that the two things are linearly, completely dependent upon one another. -1 means they're anti-correlated, meaning that when one is up, one goes down, the other one is down. That is still a strong relationship between them. If you had a function that looked like this and another function that looked like this, those are still highly correlated. Those are inversely correlated. Correlation would be -1. Any questions? Okay? So what correlation is kind of the simplest statistic that you can compute that measures how dependent one variable is on another. Okay? And it's interesting to get a feel for what does a correlation coefficient mean. Okay, that's why I show a couple of plots here. Here we show the x-axis is representing one series, the y-axis is representing another series. The dots represent a scatter plot, so that each point is going to represent the time I, where you have x sub I, y sub I is the corresponding point. If you have two series that are completely correlated, you end up getting the points fit naturally on a line, sit perfectly on a line. This is what it means for there to be a correlation of 1.0. Okay? If you look over here, this is one where it's a weaker correlation. But I think that if you look at it, it's still clear that this is something corresponding, maybe it looks like height versus width, height versus weight, or something like that, where there is clearly a strong impact. This point, that if you know the x value, you have a pretty good idea of what the corresponding y value is. This is a correlation of 0.85. Here is a weaker correlation. This was a correlation of 0.42. So what are the lines? The lines represent best fit regression lines. The line that best approximates that data by a mean of squares characteristic. And if the correlation in some sense is going to measure how far away, what is the variance in some sense, what is the error in those points as estimated by that line. This was a correlation of 0.42. This is a correlation of minus 0.33. Okay? The fact that it's minus is negative is shown by the fact that the regression line is downward sloping. Here is a correlation of 0.17. What would a correlation of 0 look like? Okay? If you look at it, these points do look highly scattered. But they're not completely scattered. If the point correlation was 0, we would expect to see more points over here and over there. Okay? Any questions? Okay? So we have a world where if we want to measure whether two-time series are similar, okay, correlation is a reasonable statistic to use. Now, one thing that's important to note is that correlation does not necessarily mean causation. Okay? One thing that you would like to do, if we think about this in a financial term, it would be very nice if, let's say this is going to be stock prices. Okay? If I had some function, okay, that I could compute or predict that had a very similar shape, okay, as that was highly correlated with a function I'm interested in. If I have two functions, one of which I know and one of which I want to know, and these functions are truly highly correlated, this enables me to give a forecast for what the value of the function is, right? I have a function I know, let's call it k. There's a function I don't know, or unknown function, u. If k and u are highly correlated, and I know k, then I can predict what u is. So one thing that people do to, let's say, in an effort to try to predict financial prices, might be to go through a large number of statistics, find out what correlates with the stock market, okay, with financial prices, and then use that as a predictor. And the trouble is that if you correlate enough time series with a target series, one of them is going to have a high correlation, sort of by chance, okay? And again, the classic example of this has to do with the stock market and the Super Bowl. How many people here know what the Super Bowl is? I don't know if any people. How many here knows what the Super Bowl is? Okay, a couple people. It is the championship of the American Football League. Okay? So there are two teams. One comes from the National League, one comes from the American League. And someone observed that for the first 20 years of the Super Bowl, essentially every year that the American League team won, the stock market went up that year. And every year that the national team won, the stock market went down. And since the Super Bowl was played in January, okay, this looked like a great statistic, right? So the reason, of course, that's silly is that just because there is a correlation, it does not imply a causation, okay? And this is something that when you do, computer scientists like doing data mining and things like this, finding patterns like this, it's important to recognize that there has to be some kind of a, let's say, causal relationship for it to be interesting. Any questions? Again, another statistic that tends to correlate with the financial markets. Google the words butter production in Bangladesh. Okay? Does anyone know Bangladesh? It's a country, right? There's a statistic that they compute, of how much butter do they make in Bangladesh each year. Okay? It's a good year for cows. I guess they make a lot of butter. Okay? What is butter? Butter is this, that's funny, Butter is a ubiquitous, it's an oil or a spread that is commonly used in the United States. Okay, it comes from cows, it's a fat from cows. Okay? What's it called here? Is it called here, anything here? Butter? Okay, butter. 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 Okay? And someone has found that basically if you correlate butter production in Bangladesh with the stock market, there was a tremendous, very, very high correlation. Correlated better than any other statistic that the UN had produced. Okay? And the trouble with something like that is, of course, the correlation is easy to observe, but it doesn't give you much of a prediction. Okay? It doesn't give you a good prediction. And what we're going to be interested in here is to try to come up with models that we hope have predictive power. So the lesson here is that correlations are meaningful, okay, if, depending upon a couple of different things. One has to do with how many pairs you test for, is there a correlation between something? So if you said, you know something, I think that butter production in Bangladesh should be affecting the stock market. If you only try doing one correlation between one time series in the stock market and it has a high correlation, that is interesting. If on the other hand you compare it to 100,000 statistics and this is the best one, that is a much less interesting correlation. That's what the first point is. Another issue has to do with the number of points in a time series. Okay? So in fact, just yesterday I had one of my graduate students was showing me, back home, was showing me some data. Okay? And she showed me that there was a correlation of 1 or -1 in a lot of different data that she was presenting to me. And so this seemed very, very good. It meant everything was either perfectly correlated or perfectly anti-correlated. But why was that? Can anyone figure out why? The reason was that she only had 2 data points. Okay? And so if you have only 2 data points, any variables are going to be either perfectly correlated or perfectly anti-correlated. Okay? So a correlation is more meaningful the longer the time series is. Okay? Again, the Super Bowl time series, when people noticed that there had only been like 20-odd Super Bowls. Now we are probably up to about 40-odd Super Bowls, and suddenly it doesn't work as much well anymore. Okay? Any questions? Okay? And of course, finally, I mean, the other question is, once you identify a correlation, the question of whether or not there should be a correlation, thinking about if there is any reason for a causal relationship, is kind of an important thing. That's what I mean by a sniff test. And finally, there are rigorous statistical tests to tell whether or not a correlation is, what the significance of it likely is. Okay, and we'll talk about that a little bit later on. Any questions? So, one way that you can measure the significance of a correlation, okay, involves knowing something about or to think about how meaningful a correlation is, okay, is to square it, okay? It turns out that if you square the correlation coefficient, you get a measure of the variance in one time series that is accounted for by knowing the other time series, okay? So if you want to get one way to interpret, let's say, how significant the correlation is, this has nothing to do with Bangladesh anymore. Okay, it has to do with, is a 0.7 correlation interesting? If you square 0.7, you get 0.49. Okay? The correlation between height and weight, if you plot height and weight over a certain population of people, turns out this differs from different populations, men and women. In the United States, I gather in the United States people, there's a lot more fat people, okay? And in that case, there's probably a weaker correlation between height and weight than if everybody is trim and in good shape. But nonetheless, if you think about it, a correlation of about 0.47, so about 0.7, correlates to an understanding that about 39% of one of these variables is accounted for in the other one. Okay? So if you think about it, if you have 2 perfectly correlated series, 1 squared is 1, 100% of the value of the second time series is a function of the first one. Okay? If you have a correlation of 0.7, only half of the variance in the in the second series is explained by this correlation. So this is an argument that you need fairly strong correlations in order to have a high predictive power. Okay, if you want to try to use one variable to try to predict another one. That's sort of what the argument here is. Okay? Any questions? Okay? So if you have a correlation of 0.3, that's certainly an interesting correlation. It means that the 2 series are related. Okay? Perhaps height and wealth. Okay? There's probably a correlation between how tall you are and how rich you are. Okay? Because if you weren't rich, if you were poor, you didn't get enough money to eat, and you didn't grow tall. Okay? But we would expect that to be a weak effect. Okay? And that just being rich does not explain your height very well. Okay? Any questions? Okay? So this gives you a way to sort of measure how much of it is, what the impact in predictability is. Any questions? Now, one consequence of correlation that is very important is one specific application of correlation has when you have only one time series. Correlation is a measure of one time series against another. But what if I give you a single time series? Okay? We can interpret, let's say, a single time series, okay, as two time series by factoring in a lag. Okay? Let's say we have a time series of n points. We shift it over by 1 point. Okay? I'm probably doing a bad job drawing it. Okay? You end up getting another time series with one less point. A pair of time series with one less point that share something in common. You can now ask how well correlated is an original time series and a shift of that time series by a certain number of periods. Okay? The lag L autocorrelation is the correlation coefficient of a series and that series shifted by L spots. Okay? I think I explained that badly, although it's not that complicated a thing. But let's say that we were considering financial prices. Okay? Let's say we had the price of, let's say, General Motors. Okay? This is the price of General Motors as a function of time, as measured by the actual stock price. How much of a correlation would we be? General Motors at one point was worth several hundred, let's say $100 a share. Now it is probably worth about $5 a share. Right? If we shift it over by 1, General Motors has been in business for close to 100 years, about 75 years. Okay, if I'm correct. If we shift this time series over by 1, okay, is there going to be a strong correlation between today's value of General Motors and yesterday's value of General Motors? Okay, the answer to that should be yes. Does everybody agree with that? Why is it? Because the years when General Motors was worth $100, we're talking about the value of the company, not the daily returns, but the value of the stock. There is a high correlation. The time when it was very high here, if it was high one day, it was probably high the next day, because the changes from day to day are relatively small. Does everybody get that idea? So when we talk about, so we would expect that stock price, stock return, stock prices themselves, the autocorrelation of it with a certain lag, a small lag, is likely to be fairly high. Does that make sense? How many people does that make sense to? How many people don't understand what I'm saying? Okay? So the autocorrelation function is going to tell us what is the correlation as a function of each possible lag. So suppose we take a time series and we correlate it with itself. Actually, maybe I'll need to give a real example now. Minus 100. Let's say the stock price, for example, 100, 90, 93. Then the treasurer absconds with something, 20, 21, 19. Here might be a price series, right? The correlation, the autocorrelation with no lag, is going to say how well correlated is this series with that series. And here it's going to be perfectly correlated. So the autocorrelation with a lag of 0 is going to be 1 for every function. For our stock price, with a lag of 1, we're going to be comparing this series with that, this series with that. And now we have one less point in each time series. But we can now compute what is the correlation function. And in the case of the correlation coefficient, and in the case of these, it's probably still going to be pretty high. I'm going to say 0.9. The lag 2 correlation would mean we sample with a difference of 2 points. Okay? And it should be clear that for any lag amount, L, until we get to the point where the two functions are shifted, so they only have 1 point in common, there is going to be some time series we can compute the correlation of that time series. And that will give us what we call the autocorrelation function. Okay? Any questions? This gives us a lot of information, as we will see, about the properties of our time series. Okay? If we have a random time series, where every time I'm flipping a coin and randomly flipping if I'm generating a stream of random numbers, what would we expect the autocorrelation function of a stream of random numbers to look like? For a lag of 0, we would expect them to be perfectly correlated, right? What about for a shift of 1? If they're really independent random numbers, there should be no information at all in basically knowing one of the random numbers to help you predict the other one. So you would expect the autocorrelation function would be then start to consist of all zeros. Okay? This autocorrelation function is, as we'll see maybe more concretely in a few slides, gives us a lot of information about the properties of our time series. Any questions? How do we compute the autocorrelation? Okay? How much time, as an algorithms person, if I give you a time series of n points, how much time does it take to compute the correlation of 2 time series of n points? What is involved in it? Basically, I have to compute the mean. We have to compute the variance. But the variance can be computed by, the mean. You can compute the mean in linear time for each series. The deviations from the mean, just subtracting it from the mean. In linear time, you can compute the variance. That much is clear. To compute the covariance, you've got to, for every pair of numbers that occur at the same time, multiply them and add them together. There's n pairs of numbers. It should be clear that the correlation coefficient can be computed in linear time for 1 lag. Does that make sense? Now, the autocorrelation function is n, correlations. Is n correlations. Okay? Each of which, in principle, takes linear time to compute. So you can compute it in n squared time using the trivial algorithm. Okay? It's interesting to note that the structure of this is basically a convolution. Okay? That you have a sum running over, you're convolving pairs of variables. There is a faster algorithm for computing these things. Okay? Using fast Fourier methods and things like that. We're not going to go into that, but that's just something to file away. Any questions? Okay. How do we think about autocorrelation functions? Okay? The visualization of an autocorrelation function, is what we call a correlogram. Okay? And what this is showing us is, this is the lag. The x-axis is the lag. And it shows us what is the correlation, between a lagged L time series and the original. Okay? Here is some data on foreign car sales. Okay? What's interesting about the autocorrelation function? In this particular value, you'll see that there is a high correlation. Okay? The autocorrelations are all positive. What does that mean? According to this, it would say that there is some predictive ability. If you want to know how many foreign cars were sold in the United States this year, if you know what it was sold 5 years ago, because the autocorrelation is high, knowing what was sold 5 years ago gives you some predictive power to predict what was sold today. Okay? Does that make sense? And again, this is kind of what the phenomena that you're seeing here is the same phenomena we talked about with stock prices. Okay? If you have a big number that is somehow, relatively consistent, the autocorrelation function for certain shifts is going to show positive values. Okay? Any questions? Now, if I look over here at the autocorrelation, I see a bump 7 or 8 years. Okay, that the autocorrelation seemed to be going up after 7 or 8 years. Can anybody think of a reason why foreign car sales in the United States might have an autocorrelation that goes higher after 7 or 8 years? Okay, that autocorrelation, that foreign car sales 7 years ago might be a better predictor than of foreign car sales today than foreign car sales 6 years ago. Okay? Anyone come up with a theory as to why that might be? So if people change cars every 7 years or so, you would expect a phenomena like that. Does that make sense? That if you have a year when people like buying foreign cars, are buying foreign cars because, let's say, the dollar is cheap, okay, or is high, okay, then they may use it. They'll try it. 7 years later, they may buy another foreign car, okay. So what's interesting about the autocorrelation function is it encodes a lot of information about our time series. That's what kind of the important point is. Some of it is periodicities, okay, like we see here, I think. Some of it is persistencies, that last year's sales measure something about this year's sales, just because there's some local trends in society about whether people, are accepting or not accepting these things. The other thing that you see on this parallelogram are error bars, sort of showing you when is it that autocorrelation is significant. Okay? And that's kind of what we're trying to show here. So this sort of shows that these kind of autocorrelations are significant. Once you get beyond 12 years or so, there's less predictive power in that series. Any questions? Okay. Give me 1 second. Okay, let me just go quick. Let me take a break here for a second, okay? Just to make sure that, let me think for a second, just because I wanted to talk about this thing. Okay, I wanted to talk a little bit, just because of your homework due today. Okay, we'll get back to talking about correlation a little later. Because your homework is due on Tuesday. One of the things you have to do in there is to estimate volatility. Okay? And one of the things that I wanted to talk about, okay, is question are measurements of are some of the models that we talk about here about how you estimate volatility. Okay? So again, we've talked in here before that volatility, okay, of a time series, price of a time series, okay, of a price series, corresponds to the standard deviation of the variance in the prices. Okay? That again, if we took a look at the returns, okay, each day, the volatility and the percentage changes, okay, volatility is measured the percentage changes, whether it's going up or down, the degree of up and down movement, okay, as a function of time. In peaceful times, we expect relatively little change, percentage change in prices every day. We know that we are living in more complicated times now, okay? And the volatility has been a lot higher. Part of what you need to do for homework 1 is to estimate what the volatility is. And we talk about 2 different ways I ask you to do it. Okay, I say one you could do is just an observed standard deviation. Look at the returns over the last year or 6 months or something like that, okay? And compute the standard deviation of this variance, of the change in returns, okay? That would give us some measure of how much up and down change we can expect. In principle, if you want to measure how much uncertainty is there in the return time series, in principle, the more measurements you have, okay, should give you a better estimate of variance. Okay? Again, I'm sorry if I had a difficult transition here. Let's go back and say this again. Our goal is to try to estimate the volatility in prices. For volatility, we are defining as basically being the standard deviation of the returns. In general, to compute a standard deviation is an easy thing. We can use a formula for it, okay? And the formula we've talked about several times. We compute the mean and we measure the absolute value, the square of the differences from that. If you want to estimate a standard deviation for if it's a function that is what we would call stationary, where the values don't change in their properties, the more points you sample, the more accurate your estimate of the standard deviation is. If, on the other hand, you're looking at something like volatility, the properties of that series are not what we call stationary. There are periods in time where the standard deviation changes, okay? There's high and low volatility periods. So what's the good thing about computing standard deviation as an estimate of volatility? The more points you have, in principle, the more accurate your estimate of what that variance will be, if it is unchanging. But if with volatility, as we have observed now, it is a function that changes over time, more recent observations should be given higher weight. And that's not what's usually done. That's not done in this way we compute sample standard deviation. Any questions? So a good model, okay, that's for computing volatility is what we would call an exponentially weighted moving average model. This is what I asked you to do in the homework. What is this kind of a model? Okay? It is going to say that the volatility today is going to be, okay, there's going to be today, there's some sort of mean volatility that always, let's say, happens. Some constant component to volatility. There is also some dependence on the recent past. That if RT is measuring our volatility, okay, at time t, that RT, the current volatility, should depend upon the volatility in some recent past. So we would like to have some kind of a function where the value of this depends upon the last several observed, okay, or not so much observed but computed values of the volatility function. So let's go and take a look at this again. If we want to figure out what the volatility is today, I claim the volatility function today should depend upon two different things. It should depend upon our recent estimate, our most recent observation of the volatility observed, the standard deviation of the deviation of the return yesterday. Okay, the return yesterday. But if there is a correlation, between the values of volatility one day and the next, our estimate of what the volatility today is should not be just the observation yesterday, It's a function of yesterday's observation and our model of what was the volatility sometime in the past. Okay? So what is this exponentially weighted moving average model? What are the terms in it? There is potentially a mean term. Okay? How much is it that contribution, just sort of a mean value of volatility? There is a dependence on our volatility, okay, as we've computed over the last several days. And there is an error term. That error term is measuring how much of a change was there, okay? A difference between our prediction and our the observed value and the prediction, okay? In an exponentially weighted moving average model, the dependence of this function is going to decrease exponentially with the history of it. Okay? Where the dependence of this is going to decrease exponentially with the history of it. So what am I trying to say? And I guess I'm sorry that I jumped to that. Suppose we have a model that looks like the volatility. Let's estimate the volatility like this. Suppose we have Suppose we want to estimate that the volatility of this thing today is going to be some function of the volatility yesterday plus some function, a weaker function, times the dependence 2 days ago, 3 days ago. We end up getting a function that looks like this. Our estimate for the value today is some constant times yesterday plus that constant squared times the day before. Okay? If this constant is something between 0 and 1, this value, when you square it, keeps getting smaller and smaller. Okay? And that's going to indicate that there is a weaker dependence in the future, the further back you get in history. Okay? And I'm very sorry about this. And this is what we mean by an exponentially weighted moving average model. For the purposes of your assignment, okay, I want you to use a model that looks like this. Okay? Here what we're saying is that the volatility today is going to be equal to, okay, the observed volatility yesterday, okay, times our estimate for the volatility yesterday times a constant, plus 1 minus that constant times the observation that we get. One of these is supposed to represent the observation. One of these represents the previous values of our model. So what is the observation? Okay? In the case of volatility, okay, if we want to measure the variance in returns, the value here is what was the percentage return yesterday. The closing price minus the opening price, okay, is going to be measured, divided by the total value. That's going to be the percentage change observed yesterday. In this model, what we're going to say is our estimate for the variance today, okay, is going to be equal to a constant times our previously observed estimated value, where lambda is going to be the impact of our previous estimate, and this is going to reflect the updating in respect to the next day's observation. Okay? Any questions about that? Okay? I apologize for this. Okay? Yes?
How can I get the max one? Because
Okay. Yeah. So what we're saying here is that if we look at something like this, this constant lambda is trading off on the fact that that how much do we weight yesterday's observation versus our model today? So how would we interpret this? Okay? Suppose, let's say we go a certain number of days ago. Okay, let's say that we start out 30 days ago. Okay, at some point, and compute an estimate of what the volatility is. Okay, over this time period. Okay? We can now update this value, okay, in the next day. Once we have, let's say, an estimate over some period of time in the distant past, perhaps by computing the standard deviation, perhaps by using the last value of the standard deviation, okay? What we're going to say is we're going to update that estimate by saying that our estimate for what the volatility is today is going to be some constant times our previous estimate, plus 1 minus that constant times the observed value today. And if we have that, then this gives us a way to update our estimate as we move through time. Okay? Let's look at an example here. Suppose we have a model like we are talking about it here, where our observed return values each day are -1%, 0.5%, 2%, -3%. Okay? If we just take this period over here, our observation of what the volatility should be is a 1% change, right? We take the absolute values of these things. Just based on that 1 day's observation, if this is all we know about the stock market was that yesterday it changed by 1%. Our best estimate for today would be that it changes by 1%. Okay? But now that we have, that's going to be our model value. V1 will be this, initially. The next day, what do we have? We have a new observation, which is our V prime series. And we also have an estimate of what the historical volatility is from here. This is what originally our V1 was set to initially. Now today we have an estimate, an observed, okay, value based on the market today, and a historical estimate which was based on this. Combining this and this by that formula gives us another estimate today. Does that make sense? And so in general, we have now what we have is we have an estimate time series, which is our estimated volatility. And we have every day a new observation. What this formula is giving us is a way to combine the new observation, okay, into our estimate. Why does this make sense to do it this way? Well, clearly today's volatility depends somewhat upon yesterday's volatility. And that is the new observation that we have here. But if we look at our notion of volatility, we'll see that it is that it is correlated. There is you do the autocorrelation function of the volatility stream. You will see that volatility today is highly correlated with what it was yesterday, and the day before, and the day before that. Here is where we're factoring that in, because our estimate for the volatility today depends upon our estimate as of yesterday, plus and our new observation from today. Okay? That is what this model is really trying to say. Any questions? And now I think I've said it properly.
Is the waste too small? Because the impression is that the volatility of yesterday is quite related to today's volatility, because the weight is just like 1 minus 0.944.
Well, what is this saying today? So let's say, in a standard model for volatility, the constant here is set to be 0.94. And what does that mean? That means that our estimate of the volatility today that we should use depends 6% on the observation yesterday and 94% on our estimate of the volatility as of yesterday. This is what's importing all past history. Now, why do we want why should the the term depend very heavily on the estimate? You're saying you're concerned. Why is it that our estimate is depending upon our estimate yesterday instead of our observation from yesterday? And the reason is because there is a high correlation in the function, okay, in the volatility function. If we were trying to predict my height day to day, okay, you could sort of say a good model for my height is going to be, my height today is going to be almost the same as yesterday's height. Okay? That if you had a predictor for yesterday's height, that's a good predictor for today. And the reason is because that the function is highly correlated. In that case, it's constant. Okay? Any questions? The interesting thing about this is, what is the dependence on each day's observation? Here you said today's estimate of the volatility depended upon yesterday's actual thing that happened in the market 6% of the to 6% extent. Because this thing was computed using the same formula yesterday. The day before's estimate is going to be, observation is going to be used 6% times 1 minus 6%. The day before's observation is going to account for something less than 6% of our total. 3 days ago, it will be 6% times 1 minus 6% times 1 minus 6%. Our estimate for today's value is going to decrease exponentially. The dependence of it on the observation from D days ago is going to decrease exponentially with D. In particular, its contribution in this case is going to be 6% times 1 minus 6%, okay, to the D minus 1. So if you implement this formula, yesterday's observation counted 6%, contributed 6%. The days before's observation is going to contribute something less than 6%. And this function is going to decay until eventually, once you get a history far enough away, the value of the volatility 3 years ago has very, very little contribution to our estimate. That's sort of what the significance of the model is. Any questions? So what's interesting about this? Okay? This gives us a model for computing volatility that is somehow reasonably widely used. That constant is widely used. The good thing about this formula, though, is that it lets you compute your new estimate every day without looking at the whole history. Okay? Today's estimate is only a function of two things: yesterday's estimate and yesterday's observation. Okay? And we don't need to actually go back and compute the whole history here. That's one of the beauties of this kind of a model. Any questions? Okay? Any questions at all about the assignment? Again, I'm sorry that I mashed this up in a rush. But next class we'll actually look at a different way of predicting volatility, which is interesting. And we'll go back and catch up on the stuff that I sort of skipped over. Any questions? Any questions about the assignment or anything like that? Okay, thanks a lot. If you have, okay, thanks a lot for your attention. And if you have any questions, please come to find me. Sorry.